So, in last class we have discussed about system of linear equations which are expressed in form of matrix equations, and we have seen that an row and row permutation, column permutation, linearly combining different rows or different columns keeps the answer or the solution vector nearly same. There is some change of the order of the solution vectors in solutions, or solution vectors are one solution element of solution vector is probably linear combination of few other elements, something like that, and we can see it from the physical perspective. That is, if we write down the equation in form of vector equation, we can see what is happening when we do row permutation or column permutation or do linear combinations of row, etc. But what happens to the matrix when we do these operations, so that their the solution remains essentially same or similar. So, this class will try to look into that thing, and this discussion will be on determinant of a matrix and its properties and applications. So, if we start looking into area of a parallelogram, for example, there is a parallelogram which is generated using two vectors a b and c d. It is in a 2D space, and the matrix formed by the columns. In last class we have seen how the column vectors can form a matrix is given as a b c d, and the area is essentially given as, this is the parallelogram which will come out of this, and the area is essentially given as AD minus BC. So, in a simple geometrical exercise we can find that if I find out area of a rectangle with A base and B height and subtract the area of the rectangle of C base and D height, we will get essentially same area, this area AD minus BC. And so, if we take a transpose of A, or we form a parallelogram using columns, say instead of A B C D, if we use the columns A C and B D, A transpose, this will be again having same area. Only thing is that the shape of this will probably change, because this line will be something like this, this line will be this will be the, so this will be the new parallelogram, but it will essentially have same area. The shape will probably change. So, this is write it A C and B D, and we can find out from the formula that the area will be essentially same. So, the columns of matrix A and A transpose gives parallelogram of same area. However, what we can write is that their shapes are different. These parallelograms are not the same parallelogram, but their area is same. Now, if we look into the same problem in 3D, a parallelogram, I consider a parallelepiped now, and this parallelepiped is formed by three vectors A1, A2, A3, B1, B2, B3, C1, C2, C3. And if we look into that, this is the particular shape, and the volume of this parallelepiped is, how do we calculate the volume? Basically, we calculate area contained by these two planes, take a cross product and take dot product, area of these two columns. First we calculate area between these two columns, and then they take a dot product with third one, and this is obtained as A1 into B2 C3 minus B3 C2 plus B1 into C2 A3 minus A2 C3 plus C1 into A2 B3 minus A3 B2. So, this is basically one particular height, A1 is height in the first direction, and this is the area in the perpendicular plane. Similarly, there is a height into area, h into area and height into area, or this comes as a dot product between height into area. And if we have a matrix formed by the transpose columns of the transpose or A transpose, for example, if we have the matrix A transpose like this, which is the columns are A1, B1, C1, A2, B2, C2, A3, B3, C3, it will have same volume, but the shape of the parallelepiped will be different in that case. Sorry. Now, the volume is the dot product of the area of parallelogram formed by two vectors with the third vector, and from a simple example we can see that for example, I have, if these are my axis x, y, z, I have an area formed by two two vectors a and b, and I take a third vector which has some component in z direction, the area will become as its dot, the volume will become with this area and its dot product, and this shape will look like something like this. This shape will look something like this. This drawing is very clumsy one, however, it is probably clear. And now, if we do a column permutation or row permutation, what will happen? If we do a column permutation, the order of the vectors will change. Right, first column is replaced with the second column. So, we will have this will be my, for example, this will be A and this will be B, and remaining this as the, this is the C, this is the C, this as the C. So, the area will have a different sense or different direction. For the area, if this is perpendicular to this plane, or if I calculate the area vector clockwise, here it will be if I calculate it anti-clockwise, here it will be clockwise, or the area will be inside the plane. Therefore, the volume will have a negative sense in terms of the first volume. And if we do the row permutation, it will be so if we do a row permutation, the x and y axis will be changed. So, this is z axis, this will be y axis, this is initial y axis. So, this will be x axis. If I do a row permutation, this is y axis. Therefore, again the area will have calculated in the same direction will have a opposite meaning. So, the value of the area will be opposite, therefore, the magnitude of the volume will be the opposite one. So, we can say that if rows of A are or columns of A are permutated, the value will be same, but this value will change the sign. If we have a case where one of the vectors are linear combination of other vectors, like I have two vectors, this is A and this is B, and C is something like linear combination of A. So, probably A magnified by some factor, this is alpha A, and a linear combination of B. So, we go along a parallel to B. So, maybe beta B here, and now this becomes the C. So, what happens, C essentially lies in the same plane of A and B, and therefore, the volume has to be 0. So, if one of the vectors, either the row vectors are linear combination of other two row vectors, or column vectors are linear combinations of other two column vectors, this is the volume will be 0. So, one question comes where you are discussing on volume and area only, and we will see it in a while. If any of the vectors are multiplied by a scalar t, the volume is magnified by the function t. For example, I have A and B, and this is the area. Now, instead of B, I multiply B by TB. So, the area becomes T times more than the actual area. So, this becomes T times T A if this area is A. This is again very simple, using simple geometry we can find it out. So, if one of the vectors is multiplied by a scalar, the entire area will be multiplied by that magnification factor. And then we come to the definition determinant of the matrix. Determinant of A or given by A within two vertical lines is equal to the volume of a box in n dimensional space whose edges are denoted by columns of matrix A. So, what is volume in n dimension? That is a question. At the very first lecture we are discussing about multi-dimensional vectors, because in a matrix equation we are multi-dimensional vectors, because in a matrix equation we are dealing with many variables, n number of variable equation, the equation system which has n degrees of freedom. So, if we have two variables, we can represent that by a vector in a 2D space. If we have three variables, we can represent by a vector in 3D space, because there are three components. We can say one component is along x, another is along y, and the third one is along z. If we have a 4 variable system, we can see the fourth one is something like another axis zeta, which is difficult to visualize, but I can say that there is another axis which is, I am not able to visualize it directly, but it is there. So, it is a 4 dimensional space. Similarly, we can go to a n dimensional space. Now, question will be, what is volume in n dimensional space? Okay, let us assume that we are okay with conceptualizing an n dimensional vector. What will be its volume? By the term volume will mean that it will be the space, measurement of the space that is contained within the space which is encompassed by these vectors. If I try to do a box using vectors and then take parallel of the vector, close with parallel of the other vector, once that will be space contained by two vectors, and we can find the area. If we increase number of vectors, then we will get an area. For 2 vectors we will get a plane, for 3 vectors we will get a parallelepiped, for 4 vectors we will get something, but that will be again a enclosed area, and we can measure its volume. And how to measure its volumes? For 2D we just take cross product and get the area. For 3D we take dot product of the new vector with the area and get the volume. For 4D we will take dot product of the fourth vector with the volume which has been given by 3 vectors in a 4 dimensional space, and get the something like volume of the 4 dimensional space of the 4D shape. So, n dimensional space, this volume may be conceptualized as a measurement of space contained within the space which is obtained by taking dot product. This space is contained by the 4 n vectors, and is obtained by taking dot product of nth vector with the space contained by in other n minus 1 vector. So, like we built volume based on previous vectors only and dot product with the present vector, and move on. The transpose matrix will have same area or same volume, except the shape will be different. We have seen for 2D the transpose matrix is giving a different shaped parallelogram. The area is same, but the order of the area is same, order is not, order is same. So, the shape will be different or the orientation will be different, however, it will have same determinant or same volume with same magnitude and same sign. Now, we come to a next thing is determinant is defined for square matrix only. Why square matrix? If we have two dimensional space, we need two vectors to define a parallelogram. So, the columns will give a square two columns of 2 into 1 order will give me 2 into 2 matrix, 2 columns of 2 into 1 matrix. So, it will be a square matrix. For 3D it will be again a square matrix. Now, if we have a diagonal matrix, the determinant or the volume measurement is very easy, it is the product of the diagonal, right, product of the diagonals. Why? If I have a diagonal matrix, the vectors are 2 0 0 0 3 0 0 0 4. This is probably 2 0 0, this is 0 3 0 and this is 0 0 4. So, each vector is the distance along one of the axes. Therefore, total area is the it's a brick shaped element now, and the total area is the multiplication of the lengths, and the total and the determinant comes to be multiplication of the diagonals. If a matrix has all 0 columns or rows, one of the vector is origin and the volume is determinant or volume is 0, and this is also very easy to say. There is an example, and if this is also very easy to conceptualize. If we have a 2D space x y and one matrix is 2 3, this is one vector, the other vector is the origin itself. So, there is no area, it is a line, the two vectors will not encompass any area and the area will be 0. So, and this can be extended to n dimensional space, that diagonal matrix will have a determinant which is product of diagonals, and for all 0 all 0 column or 1 0 row, the determinant will be 0. A square matrix with 0 determinant is called a singular matrix. In a singular matrix, at least one of the column or row is linear combination of 2 or more columns. So, it never encompasses that n dimensional space. For example, if I have two lines, one line is linear combination, means a line for 2D, this line, another line is a magnification of that. It will never make a parallelogram, encompass any area. We can take parallel of these two lines and encompass an area. Therefore, determinant will be 0. For 3D, if I have two lines and the third line belongs to the plane contained by these two lines, it will not encompass any volume and the determinant will be 0. So, for 3D it is shown, this is vector A, this is vector B, and then if I there is a third dimension, but A or B is in one plane, two vectors must be in a plane, and if I add B with a multiplication of A with a magnification of A, we get the vector C. So, A, B, C, if these are three vectors, C is combination of A and B, this is, we cannot form a parallelepiped using these three vectors. Therefore, the area volume of this will be a plane, its volume is 0, and we will see that the determinant is 0. The geometry for a n dimensional matrix, the geometry is not an n dimensional geometry and the volume will be 0. So, one question is that if there is a, we have seen if one of the row or column is 0, the determinant will be 0. So, if there is one 0 vector in row and column, the determinant will also be 0, and that shows that a 0 vector is also a linear combination of other vectors. For example, if I have A and B, I multiply 0 with A and B, I can form C, and a C which is 0. So, a resultant of multiplication of A and multiplication of B can be 0 at any point of time. So, if there is a 0 vector, it will be also a singular matrix and the determinant is 0. determinant will not change its magnitude due to row or column operations. The sign may change due to permutation, and we have seen that if we do row transpose row permutation or column permutation. In case of row permutation, the axis sense of axis will change. In case of column permutation, the order of the vectors will change, and therefore, there is a change of sign. If a matrix is diagonalized using row operation, you have seen row operation that the matrix can be changed using row operation. If by this row operation the matrix is not changing its determinant, if it is a permutation, its determinant is changing in sign, but all other row operation like combining adding one row with other row and then taking multiple of that, adding it with the third row, all these things will not change the determinant of the matrix. And if we can get a diagonal form using these row operations, the determinant can very easily be obtained as the product of the diagonal. So, here are few properties of these determinants. We have some of these we have already discussed. Determinants of an identity matrix is 1, because all the diagonal terms are an identity matrix is like this 1 0 0 0 1 0 0 0 1, as all the diagonals are 1. So, its determinant will be 1. The determinant changes its sign when two rows are exchanged or two columns are exchanged just by row or column permutation. And the determinant depends linearly on first row. That means, if first row can be decomposed, if first row can be, each element in first row can be decomposed in two terms, then we can say the determinant of this matrix is equal to determinant of these two matrices. Similarly, if we multiply each element of first row with one particular term, that is like multiplying the entire determinant that by that scalar. However, as row permutations exist, the first row can be permutated to second row. So, with any row we can do this type of operation, but we doing with only one row, and we can see that determinant can be decomposed into determinant of two different matrices, or multiplying a scalar with all the elements of one row is multiplying the scalar with the entire determinant, and taking multiplying the scalar with all the elements of one row and taking determinant of the matrix is equal to multiplying this scalar with the determinant of the matrix. And also the determinant of A is equal to determinant of A transpose. So, we will say these operations are also valid for columns, because I can change the matrix as A transpose and rows can take the role of columns in that case, or columns can take the role of the rows in that case. So, the determinant depends linearly on any row or any column, only on that row or that column. If I multiply T with two of the, like T is multiplied with one row only, elements of one row only. If I multiply T with elements of the next row only, this will be T square into that. Okay. If two rows and columns are equal, the determinant is 0. So, so this is like linear combination. Subtracting multiple of a row from another row leaves the same determinant. So, it is like taking a linear combination like of one row or multiple rows and adding it to another row or the column gives the same determinant. If A has a row of zeros, then determinant of 0. If A is triangular, then the determinant is product of the diagonal entries also. And this, if we write down the matrix, we can see it. If we think as a volume calculation, etc., we can directly see it. We can probably take an example. If I have a matrix A1, A2, A3, A1, it has to be diagonal shape. So, 0 B1 B2 0 0 B3. This is a lower triangular matrix. So, if we look into the columns, the first one is any vector A, the second one has a 0 along x. So, second one is only B is only contained here. So, A dot B is first is A cross B, and C has both 0 along x and y. So, C is only along this, maybe this is x, this is y, this is x, this is y. So, C is only along this, and if we take the multiplication, this is this area into the direction its intercept in the C. Sorry, this is C3, this should be C3, and we can find out what is the determinant here, or if we just take the determinant, we will see as these terms are 0, this will be B1 into C3, is the previous formula used for the volume. If A is singular, then determinant of A is 0, and we have seen earlier that for a singular matrix is a matrix where rows are linear combination of rows or columns are linear combination, one column is linear combination of other columns or one row is linear combination of other rows, and in that case the matrix X is equal to B does not have a solution, does not have a unique solution, because number of equations and number of independent variables, they will not match. Therefore, we cannot find inverse of A. I cannot write x is equal to A inverse B, because A inverse cannot be found out. So, if the matrix is singular, then determinant is 0 and A inverse also cannot be found out, and we can say that if A is invertible, if we can write A inverse, then determinant should be non-zero. Product rule: the determinant of product of two matrices is product of their determinant, and this is very important rule used in several calculations in linear algebra. And now, if we can write A into A inverse is equal to I. Remember, this is doable when A inverse exists, and we can write this implies that mod of A into mod of A inverse, and I is an identity matrix whose determinant is A. Determinant of A into determinant of A inverse is equal to 1, and which tells us determinant of A is equal to, or rather determinant of A inverse this tells me that determinant of A inverse is equal to 1 by determinant of A, and this is again a very important property, and this shows this particular case that A inverse is equal to 1 by determinant of A inverse is determinant of 1 by A, and of course, we have seen transpose of a matrix. The 10th property is transpose of a matrix has the same determinant, transpose of A has the same determinant of A, and we have seen it earlier that the shape of the geometry will change, but the volume will be essentially same. So, now we have to see how to calculate determinant for a large matrix and what are the applications of determinant, especially while looking into the matrix equations. So, which we will do in the next class. Thanks.